Okay, one more time with the siren, and then there it went. That's it. Okay. So last time, I guess it's not it. That's our weekly siren test. Last time we talked about section 3.1, which was association between two categorical variables. And how did we show that association? What tool did we use? A contingency thing, yeah, a contingency table, right? Or also known as remember the other word? Cross-tabulation. So cross-tabulation or contingency table we use to show association between two categorical variables. Guess what today is? Monday. Monday. Two quantitative variables. Right, so if we want to show association between two quantitative variables, then a frequency table or contingency table isn't going to work. We've got to come up with some other way to do that. There's one other scenario that we'll do later in the semester, and that's association between a categorical variable and a quantitative variable. And that one's actually simpler. All you have to do is say, well, the categorical variable defines groups, and then we do summary statistics on the quantitative one, like smoking, yes or no, and pulse. That's categorical and a quantitative. Then we just say, well, smoking is one group, non-smoking is another group. What are the summary statistics for pulse? And that's how we show association. So if we have two quantitative variables, then we need some more tools. Okay? So to start with, let's pull up some of your data. I'm going to keep this small like this without expanding the whole thing. Hopefully that's still big enough for everybody to see. That way I can write on it. This is known as a scatter plot. And that's always the first step. Plot the data. We didn't really do that when we had contingency tables. There wasn't really anything to plot. But when you have two quantitative variables, you start by plotting the data. And this is called a scatter plot. Now you had to have MA 116 as a prereq to get in here, right? So everybody has plotted ordered pairs at some point in their life. So what are my ordered pairs here? Shoe size is the X variable. This says shoe size if it's too small to read. This says height. So what I'm doing is I'm using shoe size as the explanatory variable. Ooh, get that? X variable, explanatory. So you always make an explanatory variable on the x-axis and the response variable on the y-axis. Now in this case, there's not a real strong argument for which one's which. You know, do I use shoe size to predict height, or do I use height to predict shoe size? And I guess it goes either way, right? Although shoe size is easier to get from somebody than height. They may not know their exact height, but they probably know what size shoes they wear. So you say, hey, what size shoes do you wear? And then you can get a pretty good idea how tall they are, right? So sometimes it's real clear cut, which one's explanatory, which one's response. Sometimes it's not. In this case, it's not real clear cut, but I've just made that choice that shoe size will be my X variable. Then a scatter plot is you just plot that ordered pair for each individual. So what does one single point represent? A person. That's a person. And this particular person I pointed at has a size 9 shoe and is 61 inches tall. So by going to the x-axis and then to the y-axis, you can tell both values for every point. Okay? So you'll have some of your homework problems where they say, what are the x and y values for this point? And you're just looking at the axes and figuring it out. Okay? So when you do a scatter plot, what are you looking for?
Correlation.
Ooh, there's a new word, correlation. It's actually the title of this section in the book, Correlation Between Two Quantitative Variables, or it's a subtitle, I think. That word correlation is a word in the English language that we use a lot, and you'll hear it used in a lot of different areas. And they'll say, well, this is correlated with that. But in statistics, it has a very specific meaning. And it means not just there's a relationship, but it means there's a linear relationship. So the word linear is kind of implied by the word correlation. Okay? And I'll come back to that in a minute. When you look at a scatter plot like this, do you see linear association? I see that the points seem to be going up together like that. It's not real strong, because some of you looked at it and went, maybe. Right? Whereas if I had a plot that, let me go ahead and project that on the board. If I had a plot where the points look like that, everybody would say, ooh, yeah, definitely. That looks very linear. Right? So this is what we would call strong linear correlation. This is moderate. Okay, well, formally, that correlation we measure with a correlation coefficient. When I add the word coefficient, correlation coefficient, and we call that, or we denote that with a lowercase r. So that lowercase r will always, in this class, if you see an r, you know, oh, that's the linear correlation coefficient. And I'll give you a formula for that in a minute, but better yet, I'll tell you how to make your calculator do it. Because the formula is nasty. Okay? But before we do that, let's look at some of these other plots. What this plot is, this is real small, so you probably can't read it. It says section B, sex F. So these are females from my 10 o'clock class. Right? And you see moderate relationship. If I hit page down, I'm going to have to pull the screen down because it kind of splits. This is males, right? Males from 10 o'clock class. Here's females from your class. Here's males from your class. What do you notice when I jump back and forth between those two? Okay. I think this is pretty cool. This is like animation. One of the things I find interesting when I jump between those two is that the cloud of points, let me do it this way for you guys, the cloud of points for females just seems to jump for males. So together they form a fairly wide range there, and they seem to follow the same trend. The slope of the line that would go through the female points seems to be exactly the same, right on line with what goes through the male points. Let's look at it again, a couple hundred times. See that? So there's males. Oops, I went the wrong way. That was males from the other class. There's males from your class. Right. One of the things also, not only linear trend should you be looking for in a scatter plot, or general trend, but also looking for unusual points. You see any unusual points here? Well, if you look at sort of just kind of visually think of drawing a line through here, this guy has the biggest foot, size 18 shoe of all the males. You know, by the way, where do you go to get a size 18 shoe? What'd you say?
Big and tall.
Big and tall? Well, or you have to mail order it special maybe. But this person with the biggest shoe, is this person the tallest person? No. In fact, about the same height as this guy with a size 13 shoe. So it's a little bit of an unusual point in that his foot is way bigger than you would think it would be for how tall he is. Or you could say it the other way around. He's not as tall as you would expect for how big his foot is. Right? But that's variability. Variability around the line. Okay. Logan's brother is this guy, size 16 shoe. And that seems to be actually closer to where it looks like the line would go than this guy. So that's one of the things that you're looking for. There's the online section, females. Any unusual points?
Yeah.
This point is really unusual. This one is a little bit unusual. That one's a little bit unusual. But this one, what would you say about that point? Is it unusual in the shoe size?
No.
No, shoe size is pretty much right in the middle. It's a size 8 shoe. That's about average. But for someone with a size 8 shoe, how tall would you expect them to be? Around, 64, 65 inches, somewhere in there. How tall is it? Is she? Well, it looks like 51 inches. How many feet is 51 inches? 5 by 12. 4'3". 4'3", that's pretty short, right? So they're a lot shorter than you would expect for somebody with a size 8 shoe, right? But it's not unheard of. So when you do a scatter plot, you identify unusual points, outliers. The next step is let's see if that's a real value or if it's a data entry error that needs to be fixed. So what I should do is I should contact this person that sent that one in. And these two came from the same person, by the way. They're in the same sample of 5. I can't remember whether that point is or not. I mean, if this point was also one of them, then I'd say we either have somebody who measured family members, so they were all short, or they maybe did the conversion from feet to inches incorrectly. Right? So that'd be interesting to find that out. So I will do that. Okay? There's the males. Now there's an interesting thing here. This is males from the online class. There's an interesting thing when you look at this picture compared to the picture we looked at from your class for males. Right, now I'm going to have to page back and forth quickly. So there's your males. There's their males. What do you notice different?
They're more close together.
They're a lot closer together. There's much less spread among shoe sizes. So which one of those do you think it would be easier to fit a good line through? The ones that's more spread out. The wider your range of your X variable, the easier it is to figure out where the slope of the line should go. When they're all pushed in close to the middle, it's, you can say, well, it could be, about anywhere in there. So the linear correlation coefficient gives you a measure of the strength of the linear relationship. It'll measure stronger for your class than it does for this class. So let's look at those numbers. Oh, I'll come back to this. This is putting everything together. This is putting females and males together. So you have the block of females and then the block of males, and then it's all 3 sections all put together. So I'll come back to that one. Okay? Here was the correlation coefficient for males in your class, 0.769. Here's the correlation coefficient for the males in the online class, 0.455. And we said that this one should show stronger correlation than this one. And it is. It's a bigger number. So how big is big? Well, you need to get a feel for this correlation coefficient, and what's big and what's moderate and what's weak, those kind of things. Let's use this space, I guess. First thing I'm going to do is I'm going to give you the formula for computing the correlation coefficient. But I'm going to tell you right up front, this is not a formula that I'm going to make you use by hand. You will never have to take a data set like that and compute this guy by hand. It would take forever, and it'd be really hard to make it all the way through the calculation without making an arithmetic mistake somewhere and messing it up. But it's interesting to show the formula and then dissect it so you get a feel for, well, what is the correlation coefficient? So there's your summation symbol again. X minus x bar times y minus y bar divided by Sx times Sy. And I know what you're thinking. You look at that and you go, that's cool. Right? That's what I do when I look at it. Or you might look at that and go, that's horrible. Well, like I said, you're not going to have to do it by hand. This is built into the calculator, so your TI-83 or 84 will compute this thing automatically. But it's interesting to look at this. Let me get one of those pictures back up here. Let's do your class. Let's do that one because it fits on the board. I want to get that shadow out of there. I guess I don't need that out there. Okay? So this is females in your section. Okay. Well, let's dissect this thing. First of all, x minus x bar. What does that mean? That means for a given point, you take their, what is x? Shoe size. The observation for that individual, their shoe size. Right? So if I take this point right there, what does it look like the average shoe size is? Just eyeball it. About a 9? Yeah, I'd agree. About a 9. So I'm going to draw a vertical line up through there and call that x bar. Right? So x minus x bar is this distance. It's the deviation in their shoe size for that person. Deviation from the mean. What's y minus y bar?
Height.
That's their deviation in height, right? How far from the average height is this person? Well, what do you think the average height is?
65?
Yeah, about 65. So they're probably slightly above that. It's something like about there. I'm going to call that y bar. So this distance is y minus y bar. That's their vertical distance from the mean. Right? So you got two means. The y mean and the x mean. This point, by the way, where those two lines cross, we'll need this soon enough, so I'm going to go ahead and tell you today. That's called the centroid. That's the point x bar, y bar. And Wednesday's lecture, we'll talk about how the line of best fit must go through the centroid. And actually, when I think of drawing a line through there, it looks like I missed on my point right there. I think my y bar is maybe a little bit too low. So let me fix that. Think of drawing the line of best fit through there, it's probably going to go about right there. The line would need to go through that point. So I'm going to shift my y bar up just a little bit. This is the magic of television. I can change it if I want to. Okay? So we have deviation from the x variable, deviation from the y variable, and we multiply them together. Then we're dividing by Sx and Sy. Well, if you block these off, what does that guy look like? That should look familiar to you. If you take an x value, subtract the mean, divide by the standard deviation.
Standardized score.
Standardized score, which is also called a
Z-score?
z-score. So this is z sub x. And then obviously, what is this one? Z sub y. So all I'm doing is I'm taking a person's height and their shoe size. So let's say this is Amy right here, right? You wear a size 12 shoe, Amy? No. Okay. Well, you do now. This is Amy, right? So I calculate her z-score for her shoe size, her z-score for her height, and I multiply those two together. Then I do that for every female in this data set, and I sum them up. And then this dividing by the n minus 1 is just getting the average product. Okay? Easy enough. Well, when I draw these two lines, the horizontal y bar line and the vertical x bar line, I've divided my graph into 4 regions. We'll call those quadrants. Right? You've heard that term in algebra class probably. Although back then, quadrants were defined by the axes, but I'm defining them by the centroid. No big deal. This point, will it have a positive or negative z-score for x? Positive, because it's to the right of the x bar line. So it's deviation x minus x bar, which I erased, but this distance there, that's going to be a positive distance. What about the z-score for y? Will it be positive? So what I have, when I multiply these two together, I have a positive times a positive. When I multiply a positive times a positive, I get a positive. Right? Let's take this person. Is their x z-score positive or negative? Positive, because they are bigger than the mean. They have a bigger shoe size than the average shoe. Right? So positive x. Now what about the y?
Negative.
Because they are shorter than average. Right? Everybody see that? So y minus y bar is going to be a negative number. So this quadrant, I have rid of this. I've got a positive times a negative, which equals a negative. What about a point over in this quadrant? Negative, negative. So negative, negative is positive. And up here?
Negative positive.
Negative, positive, which is negative. Okay? So I've got some positives, I've got some negatives. And the formula says I'm going to sum those up. So what happens when you sum positives and negatives?
Depends on which one's bigger.
The negatives should counteract any that are positive, and vice versa, right? So when you look at this graph, are most of the points in the positive quadrants, or most of them in the negative, or does it just look like they're all over?
Most are the positive.
Most of them, I would agree, are in the positive. There's only 2 points that are down here in this negative, and there's about 8 or 10 that are in this one. All the rest are in the 2 positive ones. Okay? So when I sum this up, I'm going to get a positive value, because I'm summing more positive numbers than I am negative numbers. Now algebraically, I could prove to you, I'm not going to try, but it's actually a fairly easy algebraic proof that we have this relationship. That the biggest r can be is 1, and the smallest it can be is negative 1. So think about a picture where if there's my centroid point, I have points going down like this. Most of the points are in the 2 negative quadrants. So I'm going to get a negative relationship. So a negative correlation slopes down. A positive correlation slopes up. Just because of where the positive and negative quadrants are. Okay. If I start squeezing these points and pushing them in towards the centroid, eventually I push all of the points out of the two negative quadrants and all of them into the two positive quadrants. If I keep pushing till they fall on an exact straight line, then I maximize R at positive 1. If I push them so they're all in the negative quadrants, then I get a perfect negative correlation. So on the extremes, this is known as perfect correlation. In real life, you'll never see data with perfect correlation unless you did some kind of trivial research. Like, suppose I'm going to do a research on temperature. So you go out every day for 3 months and you measure the temperature in Fahrenheit and you measure it in Celsius. And then you plot those points. Well, let's see. Celsius is a linear function of Fahrenheit, right? You were given that formula in science class that, I don't remember what it is, something like C is equal to 5/9 times F plus 32 or something like that. F minus 32. It's a linear function. So they are going to fall on a perfectly straight line. But in real research, it won't be perfect, but you can get points or a correlation that's very close to 1 or very close to negative 1. Now, let's take, let's add some points to this plot. So I'm adding some in the negative quadrants. Now I've got roughly equal number of points in all 4 quadrants. What would that add up to? I've seen a few people mouth it. You're acting like, I have no idea. Well, if I have just as many negatives as I do positives, and they're roughly the same magnitude, same distance from the centroid, then they're going to add out. The negatives and the positives are going to add out, they're going to add to 0. So, correlation of near 0 is no linear association. As you get out closer to 1 in either direction, then you get stronger and stronger correlation, either positive or negative. Let me dim that projector for a second. Suppose I had a plot like that. Let me ask you first, is there an association between x and y? This is x, this is y. Is there an association?
Yes.
Yeah. Is it strong or weak? It's pretty strong. What do you think the correlation coefficient would be? What did you say? Oh, no. You're thinking something else. Just the value of R. What do you think R would be?
0. Because there's 2 quadrants.
Can't think of your first name.
Casey.
Casey, that's right. Casey, what do you think?
I said 1.
You said 1? Close to 1? I'm hearing the two extremes. Close to 0, close to 1.
Is that the regular graph or is that the centroid?
This is just a scatter plot.
Okay.
Let's say that X is the amount of fertilizer I put on my corn. Y is my yield in bushels per acre. it might actually look like this. Right? As I add fertilizer, I get better and better yield till I hit my optimum amount of fertilizer. And what happens after you put too much fertilizer on? It starts to burn the seeds and they don't sprout, and the plants don't develop right, so your yield goes back down. Right? So it comes up for a while, then it goes back down. So this kind of plot happens. Well, think about, where's my centroid at? Well, X is fairly easy. The average X is going to be about in there. But what about average Y?
Halfway up.
Yeah, about halfway up the hill.
Supposed to be where are you?
So how did my points fall in terms of positive and negative quadrants?
Equal.
About equally, so when I add them up, 0. I'm going to get this. There is a strong association, it's just not linear. So the linear correlation coefficient, we'll say, no, there's no linear correlation. So don't be fooled that 0 means there's no relationship at all. It either means there's no relationship or the relationship isn't linear. If I add enough points to make this look like this, what would that correlation be? That would also be 0. Right? That's what I refer to as a shotgun blast. If I stand at the back of the room, shoot a shotgun, it'd probably be more circular, but you'd get just a random scatter of points with no relationship between them. In this, you'll get R close to 0. Well, as a rule of thumb, the book doesn't really give anything like this, but I always get this question, well, how strong does it have to be before we call it strong correlation? What value? So I usually make up something off the cuff. If R is close to 0, no linear correlation. If R is, say, between 0.2 and 0.45, we call it weak. If it's between 0.45 and 0.65, I call it moderate. And if it's greater than 0.65, we call it strong. But don't put too much stock in my boundaries here. Different researchers will give you different cutoffs for what they call strong. And it really depends on what your field of study is. If you're a chemist and you're doing bench science, they'll run an experiment. If they don't get a correlation of 0.95, then they that's weak. There's really nothing going on. But you get people who are doing research in education, something that's real subjective, like, you ask a third grader how they felt about today's lesson, right? You collect data, you get numbers all over the place. They're ecstatic if they get a correlation of 0.3. Right? So it just depends on the field of study as to where these cutoffs are. But this is kind of a general rule of thumb. You'll get some homework problems that'll ask you to classify it as being strong or moderate or weak correlation. Now, I only did this on the positive side, but the same numbers apply on the negative side. If it's between negative 0.2 and negative 0.45, we'd call that weak correlation. So, okay? Okay, now, back to that you can't see. Let me turn this back on. And now I have to cover up my list. How would you describe correlation between shoe size and height? For females, it's kind of borderline medium to strong. Males, it's a little stronger. For my online section, they're both weak. It's that online class again, Well, the problem with the online section was, again, they didn't have enough spread in their X direction, and that's just random chance. So sometimes you collect data and it looks weak, but you collect more data, you need to spread those X's out as much as you can. What do you think it'll be? Let me go back up to that picture. What do you think that correlation is going to be? Think it'll be stronger? Yeah, because now I got a wide range. I go all the way from a size 5 up to a size 18, and heights all the way from 51 inches to 84 inches. So I've got a wide range of points, and I've got a lot more points. I've got a bigger sample size. Any guesses as to the number? 0.8? Caitlin? Jump on that bandwagon? Yeah, 0.8. 0.85? Now see, everybody else has been biased already as to what you think it would be. Anybody think it'll be 0.95 or above? Chelsea? Anybody think it'll be less than say 0.75? Okay, here we go. 0.838. Good job. For females and males broken out, I didn't actually show you a plot of that, but the females and males broken out but combined across all sections, again, for some reason the males are stronger than the females. And I think that's probably because you get more variability in shoe size for males, so you're spreading those X's out, whereas females' feet don't seem to vary quite as much, for whatever biologic reason would account for that. Now this is probably going to be a little bit hard to see. Let me do the, make it bigger. There, can you see that okay? Perfect correlation, positive, negative. This is 0.4. 0.4, you see, is, I put that as kind of a borderline for moderate. 0.45, I think, is what I use for, it has to be 0.45 before we say it's moderate. Below that is weak. And you can see that's pretty weak. Just a few more points, and you'd say there's nothing. Right? But as we start to push the points in closer to a line, the correlation gets stronger. There's 0.8. Here is 0. There'll be a question on the test like this. Only I won't use 1 and -1. I'll probably go like 0.8, 0.4, 0, and then the negatives, and you gotta match them up. Which one's which? Easiest problem on the whole test. Very rarely does someone miss, very many points on that problem, but get good at reading these. Okay, let's pull our calculators out. And this is my fake TI-84. And this is data from problem number, I think it's 21. Yeah, problem 3.21 at the end of the section. It's on page 113 of the textbook. And this is data about the price and the weight of mountain bikes. So if you look at that table, it has two types of mountain bikes in there. It has, and that's the last column, it has column FU. No, it doesn't mean FU. It means full. That's short for full suspension. So full suspension means it has a shock absorber on the front wheel and on the back wheel. And then the next is FE, which means front end. So it means it has suspension only on the front wheel but not on the back wheel. And we're going to treat those separately. So what I did was I entered the values for the front end mountain bikes. So the question is there a relationship between how much the mountain bike weighs and how much they can charge you for it? Which is more desirable, a heavy mountain bike or a light mountain bike? Light, right? Have you ever been down to Walmart and bought a bike there? It costs like 80 bucks. And it weighs as much as a Toyota, right? You go down here to Cap's Bike Shop and you spend $2,000 on a mountain bike and you can pick it up with a finger, right? So, is this going to be negative relationship or positive relationship? Sounds negative, doesn't it? As weight goes up, cost comes down. Or vice versa. As cost goes up, weight comes down. You pay more, you get less. But that's desirable, right? So enter these into L1 and L2. And I entered mine actually backwards, which that reminds me I forgot to talk about explanatory and response variables. We did that for contingency tables, but I haven't done it for scatter plots. By convention, we let x be the explanatory variable. See how it works? So x is explanatory. Y is then the response variable. Sometimes there's a real clear-cut, one of them is x and one of them is y, and sometimes it's not so clear-cut. For mountain bikes, which one does it make sense that you could vary and then the other one would respond to that?
Vary the weight.
You vary the weight and then you change the price accordingly, right? You don't do it the other way around. It wouldn't make sense. Oh, I'm going to up the price of this mountain bike $200. Whoop, it just got lighter, right? You got to make a new mountain bike to make it lighter. So, but what about shoe size and height? Which one of those is explanatory and which one's response? They both of those variables respond to something else called growth, right? You get taller and your foot gets bigger all at the same time. So when there's not a clear-cut choice, then it doesn't really matter. You just pick one, call it X, pick the other one, call it Y. And in fact, the correlation coefficient R doesn't depend on that. You'll get the exact same correlation coefficient if you flip the two around. You will not get the same equation of a line through those points. And that's next section, but you'll see the difference when we get there. So I put price in L1 and I put weight in L2. And that's really backwards. I like to have my explanatory variable in L1 because that's the way the calculator defaults to wanting them. But it's easy to override that default, so we'll do that. How many people don't have their book, so they're waiting to see the rest of the data? Okay, let me scroll down. I forget how many total there are. Oh, we were almost there. So it looks like there's 8 values total, and you could probably see 7 of the 8. The last one's 140 and 37. Did you get the 180 and 34 above that? Okay. So everybody have the data entered into their lists? Okay. Now, to find the correlation coefficient, online there's the media library or whatever that's on Course Compass, and there's in there, if you dig deep enough, you can find instruction manuals for the TI-83. Well, here's a case where I'm going to tell you don't use those. Use what I'm going to tell you, because what they tell you to do is a different place in the calculator. It works fine, but it's a lot easier to get confused and do it backwards. And I always have people that do it that way, miss some points on the exam. People that do it my way never miss those points. So what we're going to do, once you get the data entered, push the stat button. Then go over to tests. What the book tells you to do is to go over to calc and then go one of those. Don't do that. Go over to tests. Okay, everybody there? Now, you're going to scroll almost all the way to the bottom of this list, although the list is so long, if you scroll up, it comes around the bottom. So, either way. I'm gonna go, and you go down to linreg t-test. So you push stat, then tests, then you go down to linreg t-test, and press enter. Then it wants to know what list did you put your x variable in. That's what x list means. And I put the weight, and we said weight makes sense to be the explanatory variable. I put that in L2, so I have to flip that. Yours probably says L1, L2. You'll need to reverse those. Remember how to put in L1, L2? You have to hit your second function button. So second function and then the number 2. And there's a little L2 above that. And then put Y list as L1. The rest of it we can ignore, except you do need to check that FREQ, freak, which is short for frequency. Make sure it is a 1. It should default to a 1, but sometimes that gets changed. If it isn't a 1, let me know and I can help you change it back. It's actually tough to change it back, so don't ever screw with that. It's a 1, leave it a 1. These two lines, just ignore, go down and hit calculate. And you should see this on your screen. Does everybody see those same numbers? None of these numbers make any sense to us at this point. After tomorrow, we'll learn what A is and what B is. There's an arrow beside the A. So arrow down. There's B. Keep going till you get to the bottom and you get R. So there's your correlation coefficient R. So R is equal to negative 0.8884. When you go to do the online homework, pay very close attention to how many decimal places they tell you to keep. Right? They may say 2, they may say 4, and they'll mix it up. So you got to really be careful with that. Now, is this strong or weak correlation? That's pretty strong. It's negative like we said it should be. Okay? Now, I ran out of time. I didn't get to show you how to do the scatter plot. If you want to play with it, it's under the stat plot button, which is second function stat plot. I have a spreadsheet, not a spreadsheet, a PowerPoint presentation that I use for my online classes that shows these steps on the calculator, and I can make that available to you so you can look at it and you can see the steps to do that. Okay? All right. So you have homework due tonight over the last section. Wednesday night will be this stuff. All right. See you then.
Anybody that didn't get the sign-in sheet?
Yeah.